Swayam Prabha. Digital India. Educated India.
The the thing is that you have to choose the right involute, okay, and even to get back the original curve itself, you have to choose a more specific involute. All right, so I will so let us look at this situation where I have here I have drawn this. So you see this this is the curve gamma here, okay, which is in purple, okay, and it is oriented like this, okay. So it is and I'm going to consider the portion of the curve from a gamma of S0 to gamma of S1, okay, namely this portion of the curve, right? And so for that portion of the curve, we look at the corresponding evolute, which is epsilon sub gamma. So as you know, the evolute is the it is the envelope of the normals. So you have to draw the normals at gamma S0 and gamma S1, okay, and they will be part of the family whose envelope is the evolute. So the evolute, so if you take the evolute as if you take the evolute as E sub gamma, then the evolute is this so let me show it here. It is this red curve here, that is your evolute, all right, and corresponding to the point S0, okay, you have this point which is the starting point of the evolute, and then the evolute, this red curve goes all the way down and ends at this point, which is the ending point which I'm going to consider, which is for S is equal to S1, okay. And of course, you see the tangent to the evolute epsilon sub gamma at S0 at this point, E gamma of S0 is this tangent line, and you see it is normal. It is normal to this curve, which is gamma. All right, and similarly, if you take the tangent to this curve, the evolute at the point corresponding to S1, then this tangent is it is this line, and this line is it is normal to gamma at S1. All right, so you have this picture, and what one is going to do is that one is going to take an involute of the evolute, okay, and I am going to take a particular involute of the evolute, and I have drawn that here. So what you do is that, so to fix things, the involute for looking at the involute of a curve, you have to take a segment on the curve, and then you have to keep one of the ends fixed, and imagine that there is a thread along the segment of the curve, and you have to pull it out gently. That is unwinding, and you can also do the reverse thing, which is winding, okay, a thread onto a curve, okay, with one end point fixed, okay. Either will trace the involute, okay. So what I'm going to do is that I'm taking this portion of the red curve, okay, and I am going to keep this point, this end point, I'm going to keep it fixed, all right, and I am going to gently move this point like this, okay. And if I do that, what happens is that I trace this blue curve, which is the involute. Okay, so this blue curve is the involute of E gamma, which in turn where E gamma is the evolute of gamma. All right, so I get this, and if you look at the picture, you can see that at least you can believe. I have drawn this picture a little carefully, so you can believe that this blue curve, which is the involute of the evolute of gamma, is parallel to the the purple curve, which is the original curve gamma. Okay, and this choice has been made carefully. If you had made a wrong choice of involute, you will not get a parallel curve. Okay, so I will explain about that. So you see, so this is a situation. I would like to analytically prove that you see this this involute is parallel to gamma. All right. More or less, it is. If you look at the picture geometrically, it is very clear. Okay, but then if you want to write it down analytically, this involves a little bit of a worrying about the arc length functions for the evolute and for the original curve. Okay, so you see, so how do you get the evolute? So here is the equation of the evolute. So let me show this here. This is the evolute of gamma. Okay, but when we write the evolute of gamma, we are assuming that gamma is unit speed. Okay, and that's because we want to make use of the Fronius-Array relations. And so so here you see S. So S is the arc length, of gamma. Okay, and you are writing the evolute in terms of the arc length of gamma. So the argument, which is small s, is not the arc length of the evolute, it is the arc length of gamma. You have to be careful about that. And then you have this formula for the evolute. We calculate the unit tangent vector. For that, first you calculate the tangent vector. So the tangent vector, when you differentiate, you get these two terms cancelling off. This you see, when you differentiate this second term, you get because of the product rule, you get two terms, and you see this the first two terms cancel, and this is because of the Fronius-Array relation. And I can apply the Fronius-Array relation because you see gamma, mind you, this is the Fronius-Array relation for gamma. I can apply it because you see gamma is unit speed. Okay, whenever you apply the Fronius-Array relation, you have to be careful that the curve must be parameterized by arc length, plus or minus arc length plus a constant. Okay, so in this case it's actually arc length. So if you do that, so then the the tangent vector to the evolute is, you are left with only this. All right, and so this is what you get for the tangent vector to the evolute. All right, and we want the unit tangent vector to the evolute. Okay, and for that you have to take this vector and divide it by its norm. Okay, and if you do that, you get this quantity, which is the derivative of the curvature of gamma divided by the modulus of the derivative curvature of gamma. Okay, and of course this because there is a mod in the denominator, you will get a sign. If the derivative of the curvature of gamma is positive, you pick up a minus sign, and if the derivative of the curvature of gamma is negative, you get a plus sign. Okay, so if you want to write it in one go, you write it as minus or plus. Okay, depending on positivity or negativity of the derivative of curvature of gamma. Okay, and remember, you are under the assumption that the curvature never vanishes. Okay, and also that you see that the curvature is, so mind you, curvature is a continuous function, so it never vanishes, means it's always positive or negative. Okay, and then this condition is that it's either continuously increasing or discontinuously decreasing. All right, so we have this expression for the unit tangent vector for the evolute. But again, you have to be careful. It is in terms of the arc length of the original curve. Okay. Now, what we'll do is we'll have to calculate the involute of the evolute. Okay. And to calculate the involute of the evolute, what you do is that you take you have to take a segment of the string on the evolute, and that segment of the string I am taking it for small s equal to s0 and small s is equal to s1. So basically, in this picture, I am taking this segment of the string, this segment, okay, from here to here. This is a segment of the string that I am looking at, okay, starting with small s equal to s0 and going up to small s is equal to s1, okay, and then so you see, when you have a curve and then you have 2 points on it, and if you fix a string there are two ways you can pull the string out, because you can choose either of the points to be fixed, okay, and I can either choose one or the other, and there are cases in which if you make the wrong choice, then you will not get a parallel curve to the original curve, okay. So in this case, what I am doing is that at least I will show you a general picture, okay, later, relating to an ellipse, okay, and there is an interesting question there about which I want you to ponder about, okay. So here what I am doing is that I am fixing this point on the evolute corresponding to s1, small s equal to s1, and then I am the other point corresponding to small s equal to s0, I am pulling it out, okay, and then I trace this. So then I trace this blue curve, all right, and I want to write the equation of this, this blue curve here, which is the involute of the evolute. So of course the way to write it is it's very, very easy. So you see, if you want the if you want to write an expression for, let us say a portion of the string, okay, say from here to here, that has been pulled out like this, okay, then after I pull it out, I will get this portion of the involute, okay, and corresponding to this point, which is given by small s, okay, I will get this point on the involute, which is so now when you parameterize the involute, okay, you use the arc length of the curve, okay, of which you are taking the involute. So you should use the arc length of the evolute, okay. So what we do is that you assume that the arc length of the evolute is capital S, and that depends on small s, okay, and I will assume that for and I want a reference point for which I want to keep the arc length as 0, okay. So I will assume that at s equal to small small s0, I'll assume that capital S is 0, okay, and then if I take this portion of the string that I have pulled out, the corresponding arc length is capital S of small s, okay, and mind you, if you look at it, that is also equal to this distance. That is the distance I have pulled out, okay, and mind you, this this line is normal to gamma, and it is tangent to the evolute. Therefore, how do you get this point, which is the point you want? You get this point by starting from this point on the evolute corresponding to small s, and then you have to move in the direction negative to the unit tangent vector, okay. So you see the evolute is being traced like this, okay, and therefore the unit tangent vector will be like this, all right, and you have to move in the opposite direction, okay. So the way to reach this point here is I start from this point epsilon sub gamma of s, and then I add this arc length which is capital S of small s, that is this length, okay, and I have to move in the direction which is negative to the unit tangent vector of the evolute, okay. So therefore you see you get this expression. So let me write this expression. So the expression is the involute of the evolute is the evolute plus this length s, okay, into the negative unit tangent vector of the evolute, okay. And here see, the point is I am writing everything in terms of capital S, not small s. Capital S is the arc length of the evolute, okay, which I am measuring from small s, the point corresponding to small s equal to s naught, for which I am assuming the capital S value is 0, okay. So you see, and this for the segment that I have considered, small s equal to s naught corresponds to capital S equal to 0, and small s equal to s1 corresponds to capital S equal to L, okay. And therefore for this capital S from 0 to L, okay, I am writing down the equation of the involute of the evolute, okay. And there's one more thing that you have to be careful about. I am using this these tildes here, okay, everywhere, just to say that, you know, the argument is capital S, which is the arc length of the evolute, and not small s, which is the arc length of the original curve gamma, okay. And you can remove the tilde and consider that, you know, consider the resulting things as functions of small s if you plug in capital S as a function of small s, okay. So what we have to do is that, you know, we have to compute this arc length of the evolute, and, you know, the arc length of the evolute is, you know, you have to just integrate the velocity vector, okay. The parameter is s, small s, and small s, mind you, is arc length of the original curve, okay. So you integrate this, you have to integrate the speed, in fact, so which is the modulus of the velocity vector, okay, the norm of that vector, and and you have to integrate it from s0 to s, okay. And mind you, small s varies from s0 to small s1, for which capital S varies from 0 to capital L, okay. Now if you do this integration, see what will happen is that, see, we have computed what this what this vector is, okay. This vector is here, this is the vector, okay, and I have to take norm of this, okay. If I take norm of this, the norm of the unit normal will become 1, okay. So it essentially boils down to the modulus of this coefficient, which is minus k dot by k squared, where k is the sine curvature, okay. And notice that, you know, this quantity is, you know, remember, this quantity is going to be negative if k dot is positive, and it's going to be positive if k dot is negative, and also this quantity is actually derivative of 1 by k, okay. So therefore moral of the story is, you see, you are only integrating this, all right, and with this with the correct sign here, you have to put a minus or plus. You should put a minus or plus, because after you differentiate, it will become plus or minus, all right. So you do this, then by the fundamental theorem of calculus, you will get the formula for this capital S, okay, in terms of small s. Capital S of small s is minus or plus 1 by the sine curvature of gamma at S minus 1 by sine curvature of gamma at S naught, okay. And mind you, sine curvature never vanishes throughout, so you have I mean, all the things in the denominator are well defined. The denominators are not 0, okay. So you have this capital S of small s. Now what you do is that you have to take this value of capital S of small s and plug it into, you know, this expression here, which gives the involute of the evolute in terms of capital S, to convert it into small s. Why I want to convert it into small s is because I want to show that it is parallel to the original curve gamma, which I have already assumed in small s as a parameter. Okay, that's why I am doing this. So you plug it back here. So what you get is the following. You get, so there's something else I've written in the middle that I'll explain later. So you see, you take the involute of the evolute. Okay, this is the original curve, which is evolute, plus you have to travel this distance s. Okay, and then you have to multiply by the negative of the unit tangent vector. All right, and now you want to convert everything to small s. You substitute capital S in terms of small s. Okay, and so if you do that, then I can remove these tildes. Okay, and write the expressions without the corresponding tildes. Okay, so these tildes are removed. Okay, and I get I epsilon sub gamma of small s is equal to epsilon sub gamma of small s minus capital S of small s times the unit tangent vector of epsilon sub gamma. All right, and now you see this epsilon sub gamma of small s, I substitute the value of the capital S of small s. All right, and then also you see this unit tangent vector. Okay, as I already told you, this is minus or plus of the unit sine normal, and minus is when the the derivative of the sine curvature is positive, plus is when the derivative of the sine curvature is negative. So we keep that very carefully. All right, and if you do that, essentially what happens is that you see, when you wrote this capital S of small s in that expression, okay, we have minus or plus. Okay, but then there is, outside there is this minus sign. Therefore, this leading here the leading sign will become plus or minus. Okay, and for the unit tangent part, it is minus or plus. The net effect is that it is minus. Okay, there is a plus or minus multiplied by a minus or plus. So whatever the case is, you will only get a minus here. That's very, very important. Okay, now what you do is that you plug in the value of the formula for the evolute, which is the original curve, plus you travel along the distance equal to radius of curvature along the geometric normals, which is given by this expression. Okay, and then you write this expression, which is minus of this term. Okay, and you simplify. The interesting thing is that this term and this term, they will cancel out. Okay, and what you are left with is only this constant. Okay, and of course this constant is but this constant is nothing but the sine curvature of gamma at the point which you started pulling out. Okay, and if you do that, you see that the involute of the evolute of gamma is gamma plus a constant times the normal to gamma, and that is precisely the expression for a parallel curve. All right, and it's very, very important that this other coefficient cancels out, because you see the other coefficient is a variable. Okay, for a parallel curve, it should be the original curve plus movement along the normal direction by a particular fixed distance, which by a fixed distance, it should not be a constant, it should not be a variable distance. If you had got this 1 by ks gamma of s term, that's a variable thing. Okay, so you see, you should expect these two terms to get cancelled. Okay, and the only constant that figures is this. All right, and basically what does this tell you? The involute of the evolute of gamma is gamma plus, you see, what is this? This is, if you take its magnitude, it is exactly the radius of curvature at the point corresponding to S naught. Okay, and you are moving in the right direction as given by the sine normal. And now if you look at the picture, so now you go and look at the picture, it agrees with what we have in the picture. So you see, if you started from here and then you pulled it out, okay, then you see this distance. is the same as this distance here. And this, what is this distance? This is from the point on the curve to this point, corresponding point on the evolute. But the corresponding point on the evolute is the center of curvature. And this distance is therefore exactly the, it is the radius of curvature. Okay, which is modulus of 1 by k naught. And you see, it is the same distance that is maintained throughout. Okay, so you see, you have this curve I epsilon gamma is just parallel to the original gamma by this distance. So it's a parallel curve. Okay, so so it's it's somewhat messy, but it's you can write it down. All right, but then there is an issue. And what is that? So I wanted to say something here. You see, there's something analytic that's going on, which actually one can notice, but probably we may not need it. But probably if you are doing more manipulations involving involutes, you have to worry about this. See, when you want to go from from the involute parameterized. So let me just give me a moment. Let me see, if you want to go from the involute parameterized by capital S, which is the arc length of the evolute, to the involute parameterized by small s, which is the arc length of the original curve. That is, you want to change the parameter from capital S to small s. Then you see that is the reason why when I wrote it as function of capital S, I put these tildes. Okay, and when you write it for small s, you don't put the tildes, just for that reason. Okay, see, you going from capital S to small s is very, very simple. You can write capital S is equal to capital S of small s. Okay, and we have computed what that is, and because it's just arc length. Okay, but if you want to do it the other way around, okay, there is something else that you have to do. You need small s in terms of capital S. That means you have to invert this capital S. Okay, and you see, inverting capital S actually amounts to inverting the sign curvature. So there is a process of, if you want to get the, the arc length of the original curve in terms of the arc length of the evolute, you have to invert the sign curvature. And you may wonder whether it is possible, it is correct to do that, and that you can actually do. The reason is because of the inverse function theorem. You see, you're assuming that you're assuming that the derivative of the sign curvature is either throughout positive or throughout negative. That means you're assuming that the curvature is monotonic. Okay, and so it is C1 invertible. Okay, therefore what you can do is, you see, we have this formula for S that we have derived. From that you can compute what. So you see, this is a constant. The S term is here. Okay, so if you write it out and bring things to one side, you get this expression. You get the sign curvature at small s is k0, which is sign curvature at s0, divided by 1 plus or minus k0 times s. Okay, and then if you want small s in terms of capital S, you have to invert. And why you can invert the sign curvature is because it is C1 invertible. That's because its derivative does not vanish and has the same sign. Okay, so this is a technical thing that is going on here. Okay, so if people want to do calculations, this is useful. But of course, we don't directly use it in whatever we did. But this is a fact that you have to understand, that you need to invert the sign curvature. Okay, if you want the original arc length in terms of the arc length of the evolute. Okay, so that is a fact. All right. So this is very, very important thing. Then okay. So the next thing I wanted to say is the following. So I wanted to say that if you didn't take the right involute, okay, then you wouldn't have got a curve parallel to gamma. And so this is something that one wants to ponder about. So here is something that I wanted to show you. I think here it is. So you see, we look at this picture where you have an ellipse, okay, and so I am taking this let us say you know uh, so I am taking this red portion of the ellipse, okay, and if I draw the the evolute of that, okay, then I will get this this purple curve, okay. So I will get this one, namely I will get this, okay. So this will be the evolute, all right. And of course, how does that come? That comes because you are only taking envelope of normal. So you see, you draw the normal here, okay, and then you draw the normal here, and then you keep doing this. You keep doing this continuously, and then you end up drawing this evolute, which is the envelope of the normals, okay. And you go all the way up to you go all the way up to here. When you draw the normal here, this will go down all the way up to here, right? So you see, for this red portion of this curve, you see, for this red portion of the curve, you have this purple portion here as the evolute, okay. Now what you do is, in this evolute, you take a portion of it, namely you take you take this portion of the evolute from here to here, okay, and then you fix this part, you fix this point, okay, and you pull out this point, okay, and then what happens is that you trace this blue curve here, right? So that is the involute of the evolute. And you see, this involute of the evolute is of course parallel to the original curve gamma 1, all right. Now if you had done it for this this other piece of the upper the upper part of the ellipse, okay, you would get the corresponding evolute like this, okay. And if you had pulled out this portion, okay, again keeping this end fixed, and you pull it out like this, I will get this portion, okay. So as a result, if you look at it, you see you are getting so this you see, this whole upper portion of the ellipse gives you this this piece, which is of course parallel to the upper portion, okay. Similarly, if you take the lower portion of the ellipse, and you take the the evolute and then the involute, you will get this lower portion, all right. Now the question is, suppose I had taken, so here is the interesting question that one would like to answer. Suppose I had taken only this portion and keep this fixed and pulled it out like this, I will get this pink curve, okay. And that curve is certainly not parallel to it doesn't seem to be parallel to any piece of the original ellipse. So you see, if you that is also an involute of the evolute, okay, but it is not parallel to the original curve, is it not? So physically it doesn't look parallel. For the moment it appears as if this pink portion of the curve is probably it appears it is parallel to this part. You see, it's and similarly, if you draw another thing like this, it looks like it's parallel to this part, but it's not. Okay, so there is something that is if you physically think of it as parallel, then it is not. Okay, so this is something that one has to worry about. Basically, if you have taken this whole thing, okay, and you moved it, you will get something like this. Okay, and similarly, if you took this whole thing here and moved it, you will get something like this. Basically, what you will get is, you will get cusps at these 2 points. You will get singular points. If I took if I took a point here, I'll get this. If I took a point here, I'll get this. Okay, and so on. These will all be parallel curves, physically parallel. Okay, except that if you take it the other direction, it's not kind of parallel physically, but of course fits the definition of parallel curve. See, what we are doing is we started with a curve, we took the evolute and then took the involutes. You will get only some involutes. For example, around the ellipse there are bigger curves which are parallel to the ellipse. They will not come by this process. See, by taking first the evolute, you have kind of restricted yourself. And then you take the involute, you have restricted yourself. So, this will not give, of course, all the involutes. You can, look at, there's really a lot of material on this. Okay, people, all these CAD, CAD/CAM people, etc., and people who work on, software that uses curves. I think probably even in, I don't know, animation also, they use these kind of things. So there is a lot of, it's of importance to mechanical engineers to produce involute gears and cycloidal gears and etc. Okay, and there are some. So I just wanted to tell you to look at some interesting things which will which you can read. Of course, So here is one very nice paper. Which is, so this is something that you can look at. So the curve parallel to a parabola is not a parabola, okay, and this is a nice exposition of several pages where there is a good motivation for how you get parallel curves, akin to parallel lines, okay, and everything is done in a very, very systematic way. So this is a very good, thing to look at. So this is one nice paper that I want you to look at. So you can note this down. Please note this down and have a look at it. The curve parallel to a parabola is not a parabola. So this is Max Stein. This is a very good paper. Okay. Then, so here is another very nice paper that you should go through. This is evolutes and involutes of spatial curves. Okay. And see, it appears that trying to define evolutes and involutes for space curves, still there are many things to be done. Okay, and only for plane curves things are properly done. And so there are some interesting things. But here in this paper, so you see here again, you see there is a plane. The plane curve case is kind of very nicely given. So you see, so these pictures are very nice. So you have the, you draw all the normals to the ellipse sufficiently close, and then you get this, star-like, asymmetrical asteroid, okay, which comes to be the evolute, okay. So just by drawing normals, you get close enough normals, you will get the, again here, you see you have this, this is the lemma of Pascal, okay, and this almost cardioid-like thing with an extra loop inside, okay. It's a very special curve. What I mean is this curve, like this. The speciality of this curve is that it has only two vertices, okay. So it contradicts the four vertex theorem, okay. It has only two vertices. And the reason why it's contradicting is because there is an intersection. But in spite of the intersection, it is smooth. Okay. See, it's topologically not smooth, but it is smooth, and it is given by a regular parametrization. And the reason is because at that point of intersection, there are two branches, and the parametrization separates the branches, and they are smooth actually. So this is a regularly parametrized curve. The problem is topologically it is badly embedded in the plane. Therefore, you get a node there, and it's topologically not smooth, okay, but it is actually by itself smooth. And of course, you can expect, the total curvature will be 4 pi, okay, because there are two loops essentially, all right, and it has only two vertices, okay. You have maximum curvature at this in this inner loop, okay. That's right. Minimum radius of curvature in the inner loop, and the outer loop, both on the points on the x-axis. You have the minimum curvature at the other end, all right. And see, for this curve, if you draw the family of normals, what comes out is this kidney bean shaped thing, which is called a nephroid. So this nephroid is it is the evolute of this lemma cone. Okay. Then here is another nice picture. So this is I'm wondering, here it is. So this is the usual sine curve. Okay. For the sine curve, if you draw the normals, okay, and look at it carefully, you get you get these things which are the evolutes. Okay. So you, by drawing sufficiently close normals, you can see the evolutes. Okay. So there are such nice pictures. So you can go through this paper also. And then there is something for people who, I don't know whether there are people who do CAD and things like that. Okay, so there is this very, very interesting thing, which I came across, that also you can show you. So here is another very interesting thing. Here it is. So there is this. So there is this very. I mean, this is a special class of curves called Pythagorean photograph curves. And the important thing is this, there is this nice book, okay, which has all kinds of, these are curves which can be, parameterized by polynomials or rational functions. And see, when you do any calculations using the computer, if you have polynomials, it's easy because your calculation will stop at some point. But if you have transcendental functions, then you have to use a power series and you have to truncate at some point. Okay, or you may have to use some special functions which will give you fastly convergent, series for those things. Okay, so therefore there is always some error. But if you had the curves, which are, if you are making calculations involving just polynomials, then you can make accurate calculations. So there are these curves called Pythagorean photograph curves, for which the parameterization can be given in terms of actually polynomials. So these are very, very good for computation. And so this author claims that it has a lot of applications in CAD, where you have, the more, if you have error, then when you do the machining to cut out a gear or something like that, or some profile, then the error also has its effect on how precisely you are cutting it out. Okay, and if your calculations are accurate, you can bring down the error to near zero, and you can get such accurate calculations by using these kinds of curves. So this is another interesting thing. I mean, if anybody is interested in these kinds of things, you can look at it. Okay, so yeah, so I think I will stop here.